So complex ions they're also called complex ions. The correct name is coordination compounds, but they are commonly called complex ions. Yeah. All right. And I talked about them in the previous lecture. They are a simple ion that has extra stuff added. So back in 221, we did hydrates. And so back in 221, we would have called this iron 2 chloride. And then we would have said, oh, it's got 6 waters. And that would have been a hexahydrate. That's not the correct chemistry IUPAC name, but that's what we would have called it. What this is showing is what's really happening is the iron or the copper, which is a +2 or a +3. +2 is the most common number that we're going to see. So when in doubt, go with +2, right? It would be surrounded by the water, or in this case, the ammonia and nitrogen. Could be a hydroxide. So it's either going to be, those are the ligands. So the ligands can either be a molecule like water or an anion. So we're going to learn how to name that correctly, which I do down here. So I want to go through ligands or ligands. Either way, they can have one teeth or one tooth, which would be like chloride or actually water. The tooth for water is the oxygen. And so the iron has a +2 charge. And so that oxygen in the water has an attraction. Why does it have an attraction? What do you know about oxygen?
It wants to have 3 bonds.
No, it's a great answer, but it's not. So actually, I want to go back to something. So that is this dots. The dots are not bonds. The dots are an attraction. And so the lines are bonds. They're covalent bonds. They are being shared. This is an attraction. What were you going to say, Major?
Oh, I was going to say because it's greedy.
It's greedy. So in the water molecule, you guys all learned how to do those dipoles. So oxygen's always pulling more on the covalent bond. So those are covalent bonds. But the water, it's a polar covalent bond. The oxygen is pulling more, so it creates this negative area, which we call a dipole, a negative dipole. And that negativity is attracted to the positivity of the iron. And so it would be surrounded by 6. The nitrogen would have the negativity. So when you see nitrogen, that's the NOF, where I have seaweed NOF. So nitrogen, oxygen, and fluorine, because they're so greedy, they're so electronegative. The whole Linus Pauling thing with the electronegativity chart. There's actually a new chart that a different Nobel laureate, I guess, had Nobel laureate envy, came up with a whole new chart. I personally have never looked at it because Linus Pauling's my hero. But nitrogen, oxygen, fluorine have this strong pull. You could also just have something like a chloride ion. In this case, it's just a Cl. It could be a hydroxide. So it could be an anion, or it could be a polar molecule. Then there's ones with multiple teeth. And C2O4 is a great example. Does anybody know the name of that ion? Starts with, oh, Major's like Googling it really fast. Starts with an OX.
Oxalate.
Yeah, this is oxalate. This is what's kidney stones are either calcium carbonate or they're almost always calcium oxalate. So if you have a kidney stone, you're supposed to catch it in the sieve because they want to see which one it is. But from what I understand, it's so painful. Drink a lot of water. So oxalate. How you would draw oxalate is it's 2 carbons. Carbons hook up, and then each carbon has an oxygen. I'm sorry, it has two oxygens. It has a single bonded oxygen. That single bonded oxygen has a negative, and they each have a double bonded oxygen. So carbon makes 4 bonds. That is that's like the main point of organic chemistry. Carbon makes 4 bonds. Oxygen makes all sorts of things. So it usually does make 2. And if it has the 1, it has this negative area. But because this molecule has 2 negatives on it, has these 2 areas that are negative, it would have whatever, let's say we had nickel here as our centerpiece. We would show it as 2 teeth. So it's polydenate means it has more than 1 tooth. This picture here, yeah, it has 6 teeth. This is EDTA, and I don't know where my notes are with my cheat of what EDTA stands for, but it has 6 teeth. It is used in environmental and in socialized health countries, like if you go to Canada. Rather than here, we just do a $200,000 operation where we cut the chest open and we'll do like a bypass surgery. We don't think that's drastic there because it's funded by the government, and the government, actually healthcare doesn't have any money anymore anyway, but they give you chelation therapy because most of the time it is actually calcium buildup. And so the EDTA binds to the calcium and pulls it out. You have to also be going through doctor care because they give you IV of minerals, because calcium, magnesium, it's pulling out all the ions. And so they're having to replace them in a very gentle way. EDTA was what was used during World War I for the poisonous gas Kobe talked about, the chloride and stuff. And so that's when it was actually realized it was a chelator. All right. So 2 pieces of information you're going to be asked, well, a couple, there's going to be 5 things that we go through. One is we're going to learn how to name these. We're going to get to drawing them, which is really fun. I just remember doing Lewis structures. And then we're going to get to do electron orbitals. And these guys are really, really fun to work with. We're going to do a review of oxidation numbers. And then next week, actually, after your midterm, we're going to do thermodynamics and then oxidation reduction again. And then the other piece that is new is the coordination number. It's how many teeth, how many connections are there. So like here for the copper, there's 1, 2, 3, 4, 5, 6. So there would be a coordination number of 6. So we're going to do it for each one of these. And then, sorry, I have to see where my page is going. And then we're going to name these. The rules for naming are a little wacky. So this one has a coordination number. So I'm just going to say, I'm just going to say the co-number of 4. There's 4 hydroxides. The next one with the water, there's 6 waters. So it is 6. The chlorides are outside the bracket. The chlorides are to balance the charge. So the iron has a +2 charge. Something has to balance it out. Like up here, the copper, there's a +2 charge left over. So if you see brackets, these are an anion outside the bracket. These that are inside the bracket, these are ligand or ligand. Where it drives me crazy because you hear it both ways. The next one is 6. Why is the next one a 6?
With 3 sodiums and 3
No, so the
oxalates.
sodiums are extra. The sodiums are outside of the bracket. So the only ligand we have are the oxalates. We have 3 oxalates. So why is the number 6?
Oh, because the charge of iron.
It's not the charge. The coordination number is the number of teeth, not the number of ligands. Each oxalate has 2 teeth. So 2 times 3 is 6. think we get to draw this eventually. All right, the EN, let's put it under polydenate. EN stands for ethylene diamine. Everybody just writes EN when we're writing the formula. Ethylene diamine. It also has 2 teeth. Does anybody know what's, you all actually know if you think for a moment, what's diamine mean? 2 what? Think of amino acids. When you see the word amine or amino, think nitrogen. So it's a derivative from the word ammonia. So diamine means there's 2 nitrogens. Ethyl means 2 carbons. So it's somewhat similar to this. You have a 2 carbon and then each one has an amino group. So each of the nitrogens would then have an attraction. So that would have 2 teeth. So this has 6 teeth also. And it has to do with the ethylene diamines are going to be 2 times 2 for the teeth, and then plus the 2 chlorides. The other chloride is on the outside. So we're going to ignore it for right now. We're going to add it in. But those are my numbers. 4 and 6 are by far the most common. You will run into 5. It's doubtful you'll run into a 3 or a 2. 4 and 6 are by far the most common. The oxidation number is the charge of the metal. The oxidation number is part of the name. So we said iron 2, copper 2, lead 2. That Roman numeral 2 is the oxidation number. We actually have to figure these out. OH, pretty sure you all know this from this term. If nothing else, what's the charge of OH? -1, pretty sure that. Like some people are saying, oh, I'm not very good at nomenclature. I'm pretty sure you all can do hydroxides now. So OH is -1. There's 4 of them. That gives me a -4. This is saying that overall, my whole complex has a -2 charge. So what's the charge of the zinc?
+2.
It is +2. So that is my oxidation number. Oxidation numbers do have positives or negative. So oxidation number is of the metal. It is always going to be positive because metals are cation, so +2. If you really have no idea, just guess +2 and 90% of the time you'll be right. All right, on the next one, the waters are neutral. They have no charge, but chlorines have a -1 and there's 2 of them. So that gives me a -2. So my trick worked. We're at a +2 again. I'm wondering if all of these are. All right, so the next one had the sodiums. The sodiums are not part of the complex. How can you tell they're not part of the complex?
They're outside the brackets.
They're outside the brackets. So like here, these chlorides and these sodiums, they are going to be there to balance the charge. Up here, there should have been sodiums to balance the -2. But the sodiums each have a +1, and there's 3 of them, so that's +3. Oxalates have a -2, and there's 3 of them. So -2 times 3, that gives me -6. So the iron is what?
+6.
+3.
+3.
Because the 3 sodiums balance 3 of the charge. So the iron's just +3. One other comment about sodium, and I didn't make this very clear. Coordination compounds, I thought I said this at some point, I think in the previous notes, they are the transition elements. They are the middle of the periodic table. These guys do amazing stuff. This is why when you watch, if you go hiking with a geologist or a chemist, when you see like different colors in the rock, it's an impurity of these, or the gemstones that people wear. And it has to do with these coordination compounds because they actually refract light in really cool ways. They don't actually fully know what's going on, so everything's hypothetical. All right, that chloride is on the outside. It's not going to be part of our complex, but it does affect the charge. Ethylene diamines are neutral. They have no charge. But all these chlorines do have a -1 charge. So you do factor them all in for the oxidation number. So there's 3 of them. That gives us a -3. So the cobalt is a +3. All right, so that was coordination numbers and oxidation numbers. The coordination numbers are going to be important because they're going to give us the shape. We're going to do geometry in a little bit. The oxidation numbers, these are part of the name. We're going to see them when we do the naming. So the rules are down here. By the way, so this study set and worksheet, I think I made it due Sunday. So you can do it whenever you want. Some students love this and some students are like, this, my theory is the IUPAC, so that International Union of Chemists, when they met to come up with all their rules, when you take organic chemistry, have fun. This must have been like the last day, the last hour, and they were all done. And so the rules, and they also then, there's some interesting rules. One of the rules is we're not going to say chloride anymore. This is specifically for ligands. So ligands are going to be alphabetical when you write the name, not necessarily when you write the complex, which I have here. And if it is an ion ligand, you don't say chloride, it's a chloro. If it's neutral, it has a special name, like water is aqua. NH3 is amine, spelled with 2 M's, not to be confused with amino acids, which have 1 M. I was not there. I think they didn't know how to spell amine and they put 2 M's in. All right, I was going to make a sexist comment there about who was all present, just because it would have been all men because women weren't allowed in the lab in the good old days. All right, women, yeah. It's good that we're, now nobody's allowed in the lab, doesn't matter who you are. And if you have more than one ligand, and we'll just go through the steps up here. We're going to put prefixes. There's another weird twist that comes, and we'll see when we get there. We do metal. We do cation and then anion. So that's my reminder. So when we're doing this, however, the metal is part of the complex. So this is the complex. The complex has 2 parts. It has the ligands and it has the metal. When you write the formula, the metal is shown before the ligands or the ligands, however you want to say it. And here, when you write the name, they put it after. It's like you've moved to Europe and anywhere else in the world, and they put the date before the month. And then here you're in the United States, and you have to put the month before the date. Just deal with it. It's just how it is. All right, so the zinc is going to be at the end, is what I'm trying to say, with its Roman numeral. So zinc 2. And then we would say ion on this one because there's a charge left. That sometimes happens, right? We have a negative charge left over. So all the other ones, I balanced it out with something outside of the bracket. All right. I only have 1 ion, or 1 ligand, and that's hydroxide. Anybody know what it's going to be called instead of hydroxide? We change it to an O. So it is hydroxo. Sounds like the cookie. What was the cookie's name? I can't remember now. You tell me there's 4 of them. How do you say 4?
Tetra?
Yes. Tetrahydroxo zinc 2 ion. Did I not put that piece of information there? All right, there's one more piece. I thought it was there so that I had my cheat sheet to remember it. It's like an itty bitty piece, but if, let's do it at the end. If, we'll do it here. If the complex is negative. So overall negative. So it's an anion. You have to end it with 8. Like I said, it was the end of the day, they were hungry. So it is technically tetrahydroxo zinc 8,2 ion. Okay. That doesn't happen very often. They're almost always positive or neutral, and then we don't have to worry about that. The other thing, and where the 8 comes from, is cuprate, ferrate, and that brings up the next one. So iron, you can say iron. They usually say ferrous. So if you want to go with the Latin name, you can do that, or you can go with the English name for the transition. So a lot of these, right, have their historic names. So like gold and silver, argentium and aurum, so that's, there's always some students who are like, oh good, I get to do the Latin. So iron's gonna go, we'll put that there. You can either say iron 2, or you can say ferrous. We're not going to say the word ion, but we'll get to that in a moment. All right, we're going to do the ligand. There's 6 of them. So 6 is
Hexa.
hexa, and then aqua. And then this is, I don't care. You can put a double A, or you can drop one of the A's. So hexa aqua. This is technically one word. It all runs together, but I usually write it in bits. This chloride is an anion. It is chloride. It is not part of the complex because it's not part of the complex.
Does that mean that we also don't say chloro?
That's why we don't say chloro. It's an anion that's balancing the complex's charge. If the chlorine, so actually it shows up on the 4th one, what you were referring to, Major. The chlorines on the inside are going to be chloros, but this chlorine on the outside is going to be a chloride. So, all right, so the next one, the very first word is sodium. Because it is the cation. And then my whole complex. So the complex is the anion. On the one we just did, my complex was the cation. So my whole complex goes first, and then the chloride is the anion, not the ligand. All right. So you do the oxalates first. There's 3 of them. So you would normally think you would say tri, but oxalate's special. Why is oxalate special? It has 2 teeth. So if you have multiple teeth, you don't say tri or di, you say tris. So you actually say bis, tris, tetrachis. So if you get 4 kisses, which is really 8 because you're getting everything double, but that would be 8 teeth, which would be a whole nother geometry thing. So we say tris oxalate O because oxalate has a charge. So it's not oxalate anymore, it's oxalate O. So tris is that there's 3 of them. And then we say the iron with its charge. So iron, but it technically gets the 8 because it's an anion. So iron 8,3. And I know that there's 1 or 2 of you who go, I don't like that name. It would be ferrate, would be how most people would say it. 3. So they usually do use Latin names, and that's where the 8 ending, the 8 is only if it's an anion. The iron has a positive charge, but it's part of a complex, and the overall complex, because of the oxalates, ended up with a -3 overall. All right, one more. So we have 2 different ligands. We have the ethylene diamine, which starts with E, and chlorine, which starts with C. We go alphabetical. So we say the dichloro first, and then bis, ethylene diamine, so those are my ligands. They're alphabetized by the C and the E. The di is, there's 2 of a monodenate, and the bis is there's 2 of a polydenate. Isn't this fun? All right. And then I have to finish the cobalt. Don't forget the cobalt. With its Roman numeral, which is a 3. And then back to the question Major asked, chloride after. So that's this chloride. This is the anion. It is not a ligand. These chlorines are in the brackets. They're part of the ligand. The name doesn't have brackets, it has parentheses, but if you want to put brackets, I'm okay with that. These names are like you become the best Scrabble player ever. So you do have a study set. Again, it's due Sunday. You can worry about it whenever you're bored and want to just like play with the names. And then there's a worksheet. And then the question somebody's going to ask me before I go to the next page, is this going to be on that midterm? My brain hasn't even gotten that far yet. So I don't know. It might be. It would be like 2 to 5 points at most. I might make it a bonus question because these are really bizarre, but they're really fun because of what we get to do next, which is we get to draw Lewis structures. And so let's do a quick review. This usually is done as one of the last lessons because it's a really good review for the final. If you guys don't have a final, because last year they cheated. You guys have much better integrity. So don't do what they did. All right, let's go through shapes. So, right, A is linear. We're not going to see linear, so let's ignore that. D. So if you have, this is all based on the coordination number. Let's go there first. So if you have a coordination number of 6, the shape is this beautiful shape where it is 4 and then something above. No matter how you turn it, it is 8 faces that are triangles. So it's a double pyramid, which my understanding is they actually really are double pyramids in Egypt. But if you like dug underground, I don't know. Octahedral. You know, Major, it's a real bummer you weren't in the evening group last night because Sumner did a really good discussion about Egyptian history. So it would have been interesting for his person who wasn't Egyptian, but he had a good discussion on it. All right, so if you have 6, it's an octahedral. If you have 5, which I doubt we'll have 5, anybody remember? Some of you just had 222.
The hepta?
5 is where you have this triangle in the middle and something above and something below, and we just call it a triangle bipyramid. The octahedral is really a square bipyramid, but for some reason we call it an octahedral instead, because there's 8 faces. This one would have 6 faces. All right, so the 4. What is 4? I say 4 for less. I say 4 for last. Oh, because they switch it up on us because they had to, and it's all theoretical. It's all hypothetical, really. So tetrahedral is if you have 4 of the same ligand. So this is all based on the number of ligands, right? I have to tell you, I always heard it said ligands, and then now everybody says ligands, and so I don't know when it changed. So that's why I said I don't know if it's an East Coast, West Coast. So 4 of same ligand. So like our tetrahydroxo, that would be this one. This would be a tetrahedral because they're 4 of the same. These guys all would be octahedrals because they're all 6. However, there has to be a however. If you get a 2-2 split, so you have like 2 chloros and 2 hydroxos, it actually makes the square planar. So you have 2 of like 2 chloros, and we'll do 2 aquas. I think we run into that. Oh, we see it right here. It actually flattens down. It's all hypothetical, but it has to do with the light wave, the light that they see coming off, the colors. There is actually, and I didn't do it. If you go onto Blackboard and you click on, like before you download, if you click on that link, it takes you to the YouTube. There's somebody made a 2-minute video of, I think it's this experiment. And it's much better than I could do because we don't have all the ions and stuff, but these guys make really awesome colors. And so I think he did it with nickel, so it's not this one. This one at the top, they're all chromiums, and it's just chromium with water. Well, this is iron. These are all water. These are chromium, iron, cobalt, nickel, and copper with water. And so you get different colors. And then these are just other ones. And so they make all these different colors. And whenever we see these awesome colors, it is that. All right. So an isomer just means it's the same thing, but somehow they're arranged differently. All right. Let's name these, and then we'll draw them. There is no bracket. This is neutral overall. So this is a neutral complex. So it's not technically a complexion, it's neutral. We name the ligands first. NH3 is called an amine, like for aminos, so diamine. So those are the 2 NH3, and then dichloro. And then platinum. And then the platinum gets a number. So something that happens, I think on the study set, we run into a platinum that gets a 0. You do actually write the 0 in there, so you always show an oxidation number, but that is possible. The chlorines are -1, the amines are 0, so the platinum is a 2. The 2 is the oxidation number. All right, what's my coordination number?
The 6.
4.
Oh,
So I have 2 plus 2. 6 is going to be the next one. However, I have 2 of these and 2 of these. This is going to make a flat square. So what's it called? Square planar, planar square, however you want to call it. So I'm going to make a, it flattens the tetrahedral. I don't know why. If you really want to know why, this is what Dr. Russell got his doctorate on way back in the day. So maybe he can tell you. If you're ready for a long answer. All right, you draw the platinum in the middle with its +2 or 2 plus. And then you're going to put dots in 4 directions. You can do north, south, east, west, or you can do like me, southeast, northeast, southwest, northwest. Okay, so put them in 4 directions, and now put your ligands. So the CLs are negative, So I'll just put them there. When you do the nitrogens, if they're on the left side, I didn't do this on purpose, but it's perfect. The nitrogen is what is attracted because that's the one that's electronegative. So you write it backwards. So you write it H3N. So there's 3 H's and the N is what's making the attraction. You will see this in organic chemistry. Those you had me for 222, you saw it with me. They do it also often with methyl groups. So that's one way to draw it. The other way is you put the chlorides across the chloros across from each other. And you put the aminos across from each other. So again, it is a neutral amine, but the nitrogen has a negative area because the hydrogens will take a positive. So it's a very polar molecule. If it was a tetrahedral, it would not do this. So that's why they know for some reason it changes. I'm sure there's somebody has an idea why. So those are 2 possibilities. One of them is polar and one of them is nonpolar. Which is which?
I think the second one is nonpolar.
The second one, the way I drew it, my lower one is nonpolar because the chlorides end up across from each other. In a tetrahedral, that doesn't happen, and that's part of why they know. So they are ions, so they're all going to be water soluble. This should be, this is a negative, that would be a positive. You don't have to show that, but I had a stray mark there. This one would be considered polar. There's another term for this, and that is the nonpolar one is considered trans, which means across, like the Transcontinental Railroad went across the country. And this is cis. And it's a Latin word that means something, but I always think of my students would always say they're like sisters, they're next to each other. So if that works better for you. All right, this one also is a neutral compound. Go ahead.
Sorry. So why don't we write the NH3 backward on the second one again?
We're trying to show that it's the nitrogen, not the hydrogens that are attracted to the platinum. So if we really did this right, the way you're supposed to do it is you're supposed to draw the ammonia out. So the nitrogen with the hydrogens around it. So if you like that better, you can do it like that. Or you can write it backwards like I did on there. But it's trying to show it's the nitrogen that's attracted. And again, you're using dots because it is an attraction. Does that answer your question, Major? Yeah? Okay. On this one, Tetrabromo. So we use the O because it's a ligand. There's no brackets. So again, it's a neutral complex and dichloro. So alphabetical. So the B alphabetical by the bromo and the chloro, not how many. And then iron or ferrate. Oh, what is my charge on my iron? We're gonna go with it though. All these guys have a -1, so my iron apparently is a 6, which does happen. Back when I was in school, it wasn't possible yet, but it is. There's 5s, there's 6s, there's 8s. All right, we'll go with this. So we'll give the iron a +6. I think I have a typo somewhere, but we're gonna go with it. And so you're gonna have 6 things, and they do go straight across from each. So you have like an X and then something above and below. Does that make sense? So something's always across from something. So we can get a polar, nonpolar. So the nonpolar would be you put the bromos always across from a bromo. These would all have charges because they are not neutral. So this would be our nonpolar. You can just write NP. And then of course your other choice, there's only one other way you would put the chlorides next to each other, or the chloros. So however you want to draw that. There's no other way. You've just rotated the picture. That's a spatial, like looking at things in your brain. It's not just rotating, it's three-dimensional. That's what this picture is trying to show, that some of these are sticking behind the paper. So there's only two possibilities. All right, that one's nonpolar. This one's going to be my polar. So questions with that? These would do the cis trans also. The polar is cis and the nonpolar is trans. The study set for this, I'd figure out when I'm going to videotape it. So if there's somebody who wants to be there when I videotape it, we can negotiate when I'm going to do that. Or I can just videotape it by myself and then post it like Friday or something. So it'll be a give me study set. All right. So last page. This is a lot of words because this is just using me going blah, blah, blah. But the bond it's an attraction, right? And so it's a special type of bonding. They have two different theories. One is about molecular orbital theory. You guys remember those? You guys were great at those. It's not on the final because we don't have a final. We do have a third celebration, which will be on thermodynamics and electrochemistry. So, but we're not going to have a final over the whole sequence of 221, 222, 223. If you're disappointed in that and you really wanted to try the final just to see what would happen, we could do it. We'd have to do it in person though. And apparently we'd have to wear masks now but the only reason you'd want to do that, there's some students who are like, yeah, I want to see if I could do how well I would do compared. But yeah, the second theory is the thing with crystal field theory, and it's the idea that the d orbitals are not actually all equal. So does anybody remember how many d orbitals there were?
10.
There's 10 electrons. This is the, you guys remember where I'm going, SPDF? Those of you who didn't have me, this was the Sherpa PDF. That was the order, or Sam, Paul, Dave, and Frank.
1357.
Yeah, 1357. The quantum mechanics is what this all is. That's where all our color comes from. That's so this is the number of orbitals. So D's are the ones that always filled after the next S because they have really high energy. The D's are not all equal. And so the ligands destabilize the D's. And so rather than showing them as 1, 2, 3, 4, 5, remember doing that with the d orbitals, they actually split, and you get a 3-2 split. So this is actually what they look like. The 2s are higher. The amount of the split determines the colors you see, and if it's has unpaired electrons, so is it magnetic or not? And so they know this must be right because they can study magnetism. And as those of you who've been with me, we're moving into the age of magnetics. Well, hopefully we are, because that will change everything once we get that. So the idea is they call it high and low spin. And high spin means really, this is my simple brain explaining it, but you can think of it that the electron has I mean, they always have outrageously huge spins, but it means that the split is so small that the electron, that they're all equal. So an electron just goes 1, 2, 3, 4, 5. So if we had 5 electrons, you would do 1, 2, 3, 4, 5. So it's because those electrons have enough energy to make the jump is small, it's normal. If it is a low spin, so this is like major, he's done that shot of, oh my gosh, what was it you were saying? His caffeine with lime juice. I don't promote this. This is, he didn't do that. It's one of those mornings, there's no coffee. Like, what if we go into that thing like there was no toilet paper? What if there was no coffee? And he's a low spin day. You've all been there. You've all had a low spin day. There's a big split. There's a big gap. There's no way you're making that jump. So if you have 5 electrons, you're going to go 1, 2, 3, 4, 5. They can't make the jump. It's just like, I don't have my caffeine. I don't have my green energy drink. I don't have whatever it takes you guys to get going in the morning. When you don't have your caffeine and we go into that whole weirdness thing, it's not going to happen. You sit and meditate and it all goes away. All right. You're all going to meditate for the rest of the term, because then we get extra points at the end, and do gratitude. And you can actually do more than that. You can, like, if you did the giggles like for this week, then next week you can try the gratitude. It's quite interesting. I don't know if any of you who've been with me noticed, you always had the option for meditation before. Like, it was one of the options, and suddenly it wasn't an option. There was somebody who, they didn't like say it that way, but all right, so we're going to do this. We'll write the names just for practice. So this would be, we say the potassium is on the outside. It's not part of it. Oh, this is a question nobody asked. So I will ask it to get somebody else on the board. I just say potassium back on the first page. You can go back there. It was the question I was waiting for. It's always been asked, but I think I'm going really fast. You guys are tired. Why did I not say trisodium here? Or dichloride? Or dipotassium?
Because it's outside.
It is outside. So the ones on the outside, you don't say ditri or anything. You just say what it is. Why?
Because it's ionic.
Because it's ionic, and ionic is all about just the attraction. Remember, we didn't say magnesium dichloride in this class. We say magnesium chloride. So ionic ones, that was Juan. I finally know his voice. You know, you get the like Jedi effect with your microphone, and that's what it is. It's like Yoda is talking to me, Obi-Wan Kenobi talking to me from, all right, so we'd say potassium and then tetrachloro. And then cobalt 8, because it's an anion complex. And then we need a Roman numeral. It's the Roman numeral.
4.
When in doubt, say 2. Captain America. You're already on the board though. It's not 4 because the potassiums are there. So the 2 potassium, so the chlorines give you 4, and there's 2 potassiums. That's why I was mumbling to myself. I'm sure there's a typo over here, even though you could have a 6. These guys are almost there. I've only seen 2s and 3s, and so there must be some potassiums missing. All right. The coordination number, that's the oxidation number. The coordination number is what? Only the ligands. That's the 4. You were just a step ahead. I think I was hearing your answer for this one. It's that weird time thing that happens on Zoom. All right, the coordination number is 4 and the shape is tetrahedral. Why is this one a tetrahedral? and not the planar square, flat square thing that we did.
Because it's 4 of the same.
Yeah, all the ligands are the same. They're all 4 chloros, so it actually is considered a tetrahedral. It's going to be non-polar because they're all chloros, but they're all water soluble because they're complex ions. All right, we're going to do, I said this wrong up here. If it's a tetrahedral, what I said here is correct. Down here, tetrahedrals and octahedrals split different. This is because the notes have changed over the years, and they've probably changed since I made these notes a couple of years ago. This is like a really hot field. I have no pen. Hopefully before tomorrow I get a pen. All right, the tetrahedral is a 2-3 split. What that means, so there we go. We'll just go with the green. It's a 2-3 split. It's 2 and then 3. So these are my 3D orbitals. So if we look at cobalt, if we look at cobalt on our periodic table, you guys remember doing this? It's like a blast from the past. You do the previous noble gas. We would say cobalt is argon. We're doing this for the cobalt. And then normally we'd say 4s2, 3d7. Yeah. Except because it's 7 over in the 3Ds, sorry. Scandium, right? These are my 4s's. The potassium and calcium are the 4s's, then 1, 2, 3, 4, 5, 6, 7. The +2 means you lose the 4s. So those are gone. So it's a 3d7. Tetrahedrals split as 2 to 3. I have to tell you, this is the low spin day. This is the low energy day. You have 7 electrons. You know what? It's not going to matter. 1, 2, 3, 4. The first 4 are going to feel like that. And then 5, 6, 7. It would have made a difference if it was any number other than 7, but it didn't make a difference for 7 on tetrahedral. Anyways, that's my 3d7. All right. We're going to name coordination number, oxidation number. The split is a 3-2 split, but it's a high spin. So it's not going to matter. So pick your favorite thing to do. So we have to figure out the charge of the iron. We'll do the charge, and then we'll do the whole name. The ethylene, diamine, and the water have no charge. They're neutrals. All the chlorines have a charge. There's 3 chlorines. So that gives me -3. So my iron is a +3. So normally if I did iron, I would have 4s2, 3d6. +3 means we lose 3 electrons. So it lost 3 electrons. So you always lose the 4 s's, and then it loses 1 of these. So there's only 5. Now, if this was low spin, they would all go in the, did I tell you guys what the spin was? Yeah, I did. It's a high spin, sorry. So it's an octahedral. Tetrahedral split 2-3, octahedral split 3-2. This page of your notes, this last piece is like everything. It's high, so it's 3d5 and it's high spin. So you just do 1 in each. These are both considered paramagnetic. Anybody remember what that word means?
Not that they have a single electron or
They
single
have,
orbital.
they have unpaired electrons. The second one is more paramagnetic because it has 5 unpaired. Does anybody remember the word for no unpaired? So if you have,
Diamagnetic.
yeah, diamagnetic. So I want to make a quick comment though, because that's the term that they seem to use in our chemistry book, specifically looking at this. But the word diamagnetic has actually another meaning in magnetism. And so like bismuth, if you go online, bismuth has the greatest diamagnets. I don't know, my magnetism knowledge is not very good. So means no unpaired. So everything's paired up. I think that's a question either on the worksheet or the study set. All right, let's go back and name it just for the heck of it. This Cl is on the outside, so it's going to be the end of our name, chloride. In the complex, the last part of the name is the iron. And 3. Or again, you can say ferric, because that's what iron 3 is called. Right, and then the ligands. That starts with E, that starts with A, that starts with C. You put them alphabetical. I don't know why when they write them, they just put them in a random order. So you can put them alphabetical too. So the aqua goes first, so it is diaqua. Just give yourself plenty of room, or just like put an arrow that it fits in there. And then we do the chloro, which is dichloro. And then we do the ethylene diamine. There's only one of them, so you just say the word, and it is ethylene. Oh, it must be over because my mask is coming down. Must be like the time is up. All right. And so we had 2 plus 2, and this is 2 teeth. So that's where we got the 6 from. That makes it an octahedral. And that's why we did the 3, 2, and that was a little, that's it. We got through complex ions. Any questions before I stop? Right, dress up. Don't dress up. You can dress up for when you take your test. No, it's such a bummer it's not October. When we take our celebration, you should dress up, because then you won't take yourself so seriously.